This video is about Lagrange multipliers, which is a method for finding the max and min of a function subject to some constraint. So what that means, we have a function of two variables and we're just looking at its values on some curve or something, and we want to know what its maximum and minimum are. And this occurs in all sorts of applications, and I'll try to introduce it in the context of a simple geometric problem. So let me go into some details. The situation is that we have a function of two variables, and we want to maximize or minimize this subject to the condition that we're only looking at ordered pairs that satisfy some equation. So I'll write that this way as g of xy equals 0. So I want to find the biggest and smallest values of some function, but I'm only looking at ordered pairs that satisfy some equation like g of xy equals 0. So let me be specific. I could ask you a question: which point on the line y equals 3x plus 1 is closest to the origin? So let's draw a picture. I'm looking at the line y equals 3x plus 1. So that starts here and goes up 3 and over 1. And the question was to find the point on here that's closest to the origin. It sort of looks like it's right there, but we can find this exactly. But how can this be phrased as the type of problem I was talking about? Well, the thing we're minimizing, the distance to the origin. And, well, the function that represents the distance to the origin is the square root of x squared plus y squared. That's just using the distance formula. So this is the function that we want to minimize, subject to the fact that we're on this line. So what I mean is that we have y equals 3x plus 1. Let me modify this in one way. Well, here's the equation for distance. It has this square root in there, and we can actually just drop the square root, because finding the place where the distance is the smallest is the same as finding the place where the distance squared is the smallest. So I'm going to be working with the function f of xy equals x squared plus y squared, and I want to minimize this subject to the constraint that this function g equals y minus 3x plus 1 equals 0. So that's just rewriting this as an equation that equals 0. I've just moved the 3x plus 1 to the other side. So minimizing f subject to this fact. So here is the method of Lagrange multipliers. We say, suppose f and g are functions of two variables. And let's suppose that they have continuous first partial derivatives. And we also want to assume something else, which maybe I can explain later, is that the gradient of g does not equal 0 on this level curve of all points where g is equal to 0. So we suppose all of this, we have f and g are continuous, are functions of two variables with continuous first partial derivatives. The gradient of g doesn't vanish. And we say if f has a max or min at a point x naught, y naught on the level curve, then the gradient of f and the gradient of g have to point in the same direction. So the way I write that is the gradient of f at this point is a multiple of the gradient of g at that point. So one reason that we required the gradient of g to be non-zero is sort of for this to make sense. And we should think about what this method is saying. It gives us an equation that we can solve in order to maximize or minimize f. So if we solve this equation down here, namely find all points for which this is true, namely that the gradient of f equals some multiple of the gradient of g, then we'll have this list of points, and we know that if f has a max or min somewhere on the level curve, it has to occur at one of these points that we've solved for. And incidentally, this lambda here, which is just this way of saying that the two vectors are parallel, is called the Lagrange multiplier.